All right, this is the solution to problem number 22 in the fall 2017 midterm, second midterm. We have a problem where there are two speakers that are both emitting a sinusoidal wave and they're in phase with each other. So the peak of the wave on this speaker is the same as when the peak of the wave is on this speaker, but we're now moving to a point that is some distance from both of those speakers, 5 meters from one and 3 meters from the other. And we are asked basically what is the smallest frequency for which we get maximum destructive interference between these two speakers. Well, if you guys remember, if you've got two waves that are being emitted totally in phase, but they're traversing two different distances, 5 meters and 3 meters, well, they're covering two different paths, and the path length difference between them is going to be 5 meters minus 3 meters, which is 2 meters. Now, if that path length difference happens to be equal to some multiple of a half of a wavelength, because a half of the wavelength means that the wave from one is at a peak when the bottom point of the other wave is reached. So then you get total cancellation. So if you're off by half a wavelength, one wave is always maximum when the other is minimum, and vice versa, and so they totally cancel out. And so that condition means that we need to be off by either half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, etc. And so delta L, the path length difference, has to either be equal to lambda over 2, or 3 lambda over 2, or 5 lambda over 2, etc. to infinity. So there are higher and higher multiples that are larger and larger of lambda that give us the path length equal to some whole number of wavelengths plus an extra half a wavelength. And it's that extra half of a wavelength that's left over that puts us in destructive interference. Now, if this is the case, then we know that lambda is going to be equal to 2 times delta L, or 2/3 times delta L, or 2/5 times delta L, etc. So for larger and larger values of multiples of the wavelength, that corresponds to give, being equal to delta L, that corresponds to the wavelength either being 2 times delta L or increasingly smaller fractions, 2/3, 2/5, 2/7, etc. Now, which of those is the correct one for this answer? Well, that the answer to that question is the one that gives us the biggest wavelength, because the wavelength and the frequency have a reciprocal relationship. So the biggest wavelength corresponds to the smallest frequency. Well, the biggest wavelength would be 2 delta L, because 2 delta L is certainly bigger than 2/3 delta L, which is certainly bigger than 2/5 delta L. And so the smallest frequency to meet this criteria corresponds to that biggest lambda. 2 times delta L, we established that delta L is 2 meters, is 4 meters. And so that's the wavelength that gives us that's the lowest frequency where we have total destructive interference. So now we just have to solve for the frequency, and frequency is velocity over lambda. So that's 343 meters per second over 4 meters, and we get 85.8 hertz, and therefore the answer is A. So if the lambda is 4 meters, then the wave, if it travels 3 meters and 5 meters, it's traveling with a difference in length of 2 meters, which is half a wavelength, which means that whenever the wave coming from this speaker is maximum, the wave coming from this speaker is minimum, and whenever this wave coming from this speaker is maximum, this one will be minimum, and we get total destructive interference. That's the solution.